So we're in your chemistry and we're in part 2 of your chemistry in section 3, and we're talking about batteries, or what you would call batteries would be called voltaic cells. And so there's a big difference between voltaic cells and electrolyte cells, which we found in the last section. The difference is is the barrier presenting there, this barrier that was presented in there in the electrolyte solution is going to cause an electric current to flow from this strip of metal to this strip of metal. See how it's flowing? And in the midst, you can light up electrons are coming through, and it can light up a light bulb or whatever we want there, whatever power we need. It's producing power as the electrons are coming and electricity is traveling through one cell to the other. Like if you went to your car and you have to put the electrodes on the right parts, so that all of a sudden you'll get shocked because electricity will flow through. This is what's happening right here. How amazing. Now that's the voltaic cell. Electrolyte cell in itself is where we saw the silver plating and all this, these kind of things, and how they transfer is the current all of a sudden is totally consumed. So in this here, you're trying to keep the current going in a way, because if you took off this barrier, bing, this is going to happen. So in this power source, you have a power source that's going through. In the midst of the power source going through with electrolytes, you're going to have something happening between, and it's going to be, the current is going to be consumed. In the voltaic cell, the current is going to be produced. You're producing a current to produce light, and it's going to be consumed. See the difference between electrolyte cell and the voltaic cell. So that is, that is pretty important that we know that. So let's go here. The signs of a cathode and anode. So the anode of the electrolyte cell is positive, whereas the anode of the voltaic cell is negative. That is something else. So basically, why is it negative? Remember, because one's more negative than the other's negative. So they're both negative. So you're going to have that question. However, the conditions are true of both electrolyte and voltaic cells. So let's look at this summary. So oxidation occurs where? Remember, they're both vowels, oxidation, anoid, or anox, right? And reduction, red cat, or two consonants, occurs at the cathode. So at the cathode. So we have cathode and anode. So we have the ions are attracted, the cations are attracted to the cathode, and in the anode, the anions to the anode. And so this is the electron movement now is going to be into the cell and out of the cell. So we're talking about, this is the electrode conventions here, the whole thing. And the half reaction is going to be at the cathode, of course. It's going to be cathode is consonant reduction, anode is oxidation. And the sign in the electrolytic cell, this is the difference. We have in the electrolyte cell and we have in the voltaic cell. Well, the sign in the cathode, the sign is going to be negative into a positive anode, right? Because remember the sign, because negative is drawing in the cations, so it's negative. And the anode is going to be positive. But the sign is going to be reversed now in the voltaic. This is the key. So these are the difference between the two. The sign is going to be reversed, and it's going to be positive in the cathode and negative in the anode. So, so the anode, so both are similar, but the apparent sign contradiction arises because the electrons are willingly lost. I like that. They're willingly lost at the anode in the voltaic cells, while they're forcibly lost in the anode in the electrolyte cell. So anyway, the rest of the chemistry is the same except for this here. The electrolyte is basically that sign. It's kind of weird that they're willingly lost in the voltaic cell and they're forcibly lost in the electrolyte cell. Similar to this. They're going to be forcibly lost in this. Now they're willingly lost in this. I like what they use there. So let's go on to example. So the question is, a voltaic cell's half cells are iron, an iron ion there of 3 plus 3, and a magnesium, which is another, magnesium is plus 2. So they're both, they're both going to be wanting what? They're positive, so they're going to be wanting electrons, So write the reactions occurring in the half cell and write the overall reaction and tell which half cell is the anode and which is the cathode, and calculate the standard. Okay, this sounds like a lot of stuff, but let's just go over. It's not going to be as hard as we think. So according to the table, magnesium is a stronger reducing agent than iron is. Magnesium is stronger, according to our table, is a stronger oxidating agent or reducing agent. And then iron is a stronger oxidizing agent, more readily reduced than magnesium. Therefore, magnesium will be oxidized and iron will be reduced. So we have two metals, and one is more negative than the other, right? Or less positive than the other in this situation. If it's less positive, it's more negative. Magnesium is going to be more negative because it's less positive. So anyway, we have magnesium is going to, magnesium plus the 2 electrolytes would be magnesium. So magnesium is losing those 2 electrolytes. And then reduction is the iron is going to want 3 electrolytes, right? So in the midst, that would be the 2 different parts of it. Going on, the overall reaction is the sum of the half cell reactions. To balance the electrons, we must multiply the oxidation reaction by 3 to balance it. Basically, we're going to look down here. We have 2 electrons and 3 electrons. Well, to balance them out, we're going to change them both to 6s, right? So, and this, all we're doing is balancing the equation. So here we have, because 3, we have 2 here, well, 3 times 2 is 6, so we're going to add 3 to the magnesium, and to the iron we're going to add 2 because there's 3, and 2 times 3 is 6. We just want them both to be 6, and then we're going to have 6 electrons. This is what we're balancing. We need 6 electrons on both sides to be balanced. And this is going to be our net. Now we can get rid of those 6 electrons, 3 magnesium, 2 iron, and it's going to equal what? 3 magnesium ions and 2 irons. So basically the iron's going to have ions on this side, magnesium has ions on this side. So okay, so we have that. The next says to tell which half-life is the anode and which is the cathode, since oxidation occurs at the anode and reduction occurs at the cathode, right? A and O are anox or red cat. Remember those 2 things? Anyway, we have magnesium half cell is going to be the anode, and the iron half cell is going to be the cathode, because here we have magnesium is going to be the oxidation, so it's going to be what? At the anode, A and O, right? Reduction is going to be at the cathode. So, okay. So the sign of the standard reduction potential for the magnesium half cell must be reversed. We're going to have to reverse this sign. Although it's more negative or less positive, it's more active. So the more active one's going to reverse its sign. So, and then we're going to find that out. Reversing, let's look at the total problem here. So you have the 3 magnesium here. This is what we just developed above, right? Those 2, this one, and this is our net. We took the magnesium, we took the iron, and put them all down here. And now we want to know that E. This is the E, or the compared to hydrogen, right? This is how active. We want to know what these volts are, because we want to know how many. We really want to know how active. We want to know how many volts we're going to get out of this battery, right? So here we have magnesium, and it's going to be 2.36, And we have iron is a negative 0.4. And so in the midst, we're going to add these up and we get 2.32 volts. So where do we get these numbers? Well, not out of our head, that's for sure. We're going to get them from the list. So where did we get this from this list? We needed magnesium, which we have magnesium 2 plus, negative 2.36, but because it's going to react oppositely, we're going to change that to positive. And so, and what did we get for iron? So iron here, 0.44, so negative. So what did we get? For those that can't remember what numbers we had. I was really going slow here, I'm sorry. Okay, here we go. So here we go here. Negative 04.04 was the iron, 3 plus 0.044. So here we go. We basically took it as 0.04, and so we just added them together. It's very weak in voltage there, but as we add them together, because the magnesium changed, we have a volt of 2.32. Just adding up those numbers. But anyway, I just want to show you where we got those numbers. So let's go on. Okay, we're going to go on to the battery. Okay, I'm not going to really go over this. You're going to have to read this whole thing out. It just tells about all the different kinds of metals and all the different kind of batteries we have, and whether they're chargeable and are non-chargeable. But let me go over just a little bit what you can get out of this with the batteries. Let's see. I have my notes here. Hydrogen, fuel cells. Okay, batteries. Okay, here we go. So, redox reactions are used to provide portable sources of electrical power in what is commonly called batteries. Technically, these electrochemical cells are batteries only when more than one of them are connected in a series. Then we call them batteries. That's how we need more than one battery, right? And they're all used to power items ranging from pacemakers, hearing aids, watches, flashlights, automobile starters, all are batteries. So let's kind of go over a little bit. First, we have the non-rechargeable batteries that after a while they wear out and you have to throw them away and change the batteries, you know? So first of all, they have the carbon zinc cell. It's called, the zinc cell is called Leclanche cell. So it's a Leclanche cell is the carbon zinc. And it has electrolyte, this ammonium chloride is the weak acid. So it has acid in it. It's going to break it open, the acid would get onto you and eat your skin. So don't break open a battery. But these Leclanche, they have basically the carbon with a cathode there and going on. They put together and the zinc reacting, how we had before. Here's the zinc reacting. Similar as what we've done before. It says the cathode reaction is complex. It gives the whole complex equation there for the zinc chloride. This is a zinc chloride. This first one, the Leclanche, is actually a carbon round surrounded by MnO2 and a powdered carbon as the cathode. So here we have that. Let's see, here's a picture, see if we have, this is the zinc. So the zinc is the zinc serves as in the midst of it. You can see how it does. A more advanced design is the alkaline dry cell. So there's another kind of cell. So a more advanced design is the alkaline design cell, and it's a zinc anode 2 with the carbon, but it uses potassium hydroxide, instead inside of it as the acid involvement, potassium, and it can last longer, 4 to 9 times as long as the rather Leclanche one that with the zinc with the MnO2. So you can take these 9 volts and you can stack them up in the midst. So you have the alkaline dry cell, you have this zinc chloride cell, and you have the Leclanche cell. There's like 3 different kinds of cells there. Anyway, let's look here. Here's the carbon zinc cell, picture of it. The zinc the plastic vent at the seal, the outer shell. There's this side is where the anode is. And there's where the paper is. Here, the separation thing that we had before. Remember, we had to have the separation, and this is the cathode mix. So you have the cathode mix here, and that's MnO2, and you have onto this positive electrode in the carbon rod here. So basically coming through, it's just designed similar to, you know, our batteries that we designed in class, right? So, and then the electrolytes. And this one here is an alkaline cell. It's a little different, and here you can see it has a steel can here, cathode mix here, same mix, cathode mix here, porous separator here. Separator is a little different here, where we're paper separated. Now we have porous separated. Then we have the anode, which is the zinc with the potassium hydroxide here. And then we have this negative, this is where the negative electrode is. It's like a brass pin. So it's a little different than here. Here we have the positive electrode in the beginning, or in the middle, I'm sorry. And then here we have this nylon seal at the end and this steel covered plate. This is an alkaline cell. It's the same principle, just different in its chemical acid in a different way is put together, similar to the electrolyte cell of the zinc. So carbon zinc cell and the alkaline cell, a little bit different there. Here we have another cell. This is a silver oxide cell. So the silver oxide cell uses silver and oxygen, of course, at the cathode instead of the MnO2, manganese, or whatever, oxygen. And so the silver oxide gives you a longer life, and it's really tiny, like button-sized. And it's used in watches and in hearing aids and such. So here's a picture of it. The battery, as you see here, has a little rubber gasket separator. The cathode is down here with the silver oxide and carbon here down here. And then we have the anode with the zinc and the potassium oxide here. So here you have one side and the other side, steel cap. How they put that little tiny thing together, but they're putting together a battery for us, right? So just remember, it has to do with silver now, with silver oxide. And then going on describing, here's the button size here. Let's go on to the continuation here. Okay, we're going to describe this fuel cell, but we're going to talk about the lithium cell here. And it's used in, lithium is very, very reactive. So it's used in high power, lightweight, and long life things like smoke detectors and cameras and electronic locks and pacemakers. So lithium cells typically use lithium as the anode, and MnO2 are ferrous sulfate, which is iron related, as the cathode. And so, and then the electrolyte here is CH6CO3. This whole thing here is electrolyte. It's an acidic type of acid there. And so on to rechargeable batteries. So how do they recharge? Well, the rechargeable batteries, when the reactants are used up, they stop, right? And so now we have to recharge them by the electrical, usually by forcing them backwards. So we have to change the electrodes and make them go backwards, back to where they were before. And so the lead acid cell was the oldest type of rechargeable cell, and the lead is on a lot of cars and trucks. And the 12-volt batteries, basically leading them, the lead going back, and 2 volts each going back into their regular state. So the anode is like the spongy lead, and it reacts well going back, and it kind of describes here how it's with the lead, Pb being lead. Here's the anode with the sulfuric acid again, and the electrolytes in the cathode, and then how you change that, how they change that to be able to go back and reverse it. Some of them are reversible. Some of these reactions will be reversibles, and others not. So the electrodes are reversed, and then they're regenerated, and they're able to do that with the lead. So that's one of the first oldest rechargeable. But we also have a rechargeable with nickel. And so nickel and cadmium and nickel. And so here's the equation here for you. If you want the equation, we have nickel hydroxide here in the midst, the cathodes. But these are reversed during the charging, so they can reverse the nickel. And even lithium cells can be recharged now. So let's go on to this last cell right here, the fuel cells. So one of the most interesting types of voltaic cell is the fuel cell, and it's also known as the flow battery. So here's a picture of it right there, the hydrogen-oxygen fuel cell. It's important because in the future we may be using these. So it oxidizes hydrogen. The reason it can keep going is because of the hydrogen-oxygen keeps going through, and as the hydrogen-oxygen, especially in air, as it goes through, it can actually keep going, and it doesn't stop, so it doesn't wear out. You don't have to change the battery. So it oxidizes hydrogen at the anode and reduces oxygen at the cathode, and this provides a steady flow indefinitely. So, and these are used, see how it is with the hydrogen supply coming in and the oxygen supply coming in. And as the hydrogen and oxygen supply come in, this electrolyte in here is constantly charged up. And they use this for things like space travel, might be one. Used for the U.S. spacecrafts in the Gemini capsules. And because of the hydrogen and oxygen fuel gives them power. So, and these kind of things. So hydrogen and oxygen fuel cells are power. In the 1960s they used these, and these are advanced fuel cells, have been used in some motor devices. So it might be. They don't have this perfected quite yet, as you can see. Otherwise we'd be using them all the time. So let's go to the questions, and then we'll be done with chapter 16. I'm not going to do the review, the whole review, but I'm just going to go over the review in this section, which the first is, what is a voltaic cell? Well, we know that. It's a device that converts the chemical potential energy of spontaneous redox chem reactions to energy. So it's basically bringing forth this energy, and we have the voltaic cell, being, as we has with that separation, that it's forcing electrons through a wire. So the next question says, what does a metal's position in an activity series indicate about the chemical properties of that particular metal? Well, some metals, of course, are more negative or less positive, and those are very active, as they want to, they want to be able to convert quickly. And so they indicate a lot of properties about the negative, about the metal, because zinc, especially being more negative, that zinc more active would have a stronger negative charge and be used in an electrolyte solution easier than one that you wanted to be more active, right? So it depends on what metal. So what is the purpose of a salt bridge in a voltaic cell consisting of separate beakers? Well, the salt bridge is going to be that place where they separate it, so it just doesn't, the reaction doesn't boom, just happen so quickly. They're going to force the electrons out, but instead of having like a cardboard between, the salt bridge is going to apply that bridge of separation, where basically, the acid or the electrolyte solution can get through it, but the metals can't. And in that way, And controlling that, you can control the electricity that goes through, the electrons going through the wire. It says, why is a salt bridge unnecessary in a single beaker voltaic cell? Because a single beaker voltaic cell has that other barrier of cardboard, right? The salt bridge actually replaces that barrier, and so they don't need that barrier anymore. So it takes the place of that porous divider there. And with the salt bridge, there's less mixing of the solution, and so the batteries will last longer with the salt bridge. Oh, corrosion. I didn't really go over corrosion. Let's go over corrosion. It says, what is corrosion? It's electrochemical deterioration of metals. Why do some metals deteriorate? Because they're going through this same process with oxygen, you know. So let's go back to corrosion. Kind of skipped corrosion. I should have put it probably in the beginning here, because here we go. There's a whole article on corrosion. Corrosion. It says, each year in the United States alone, billions of dollars are spent to repair and prevent the damage of metal parts that are caused by corrosion. And corrosion, here's your definition, is the electrochemical deterioration of metals. The most familiar example we have is in the rusting of iron and steel. But corrosion also manifests in other, like silver, tarnishes, and green patina develops on copper, brass, and bronze. And these are all corrosion, you know. So the reactions involved in corrosion of iron are quite complex, but they're believed to occur in the following steps, okay? They're going over the steps of corrosion here. Let's, as for the steps, basically I'm not going to go through the steps, but you can see you have the anode reaction first here, and then you go on with the oxygen. Very much, as you can see, oxygenation. Oxygen is actually coming in at the same time and combining with the iron. So you need oxygen, you need air. The reason it's corroding is because the metal is in contact with the air, which has oxygen in it. So here it is right here. So I'm not going to go over the whole process of that, because you can see it's pretty complex. So here you have some steel, and you have a place where it's starting to erode. And as you erode, how the rust settles in. So you have the iron reacting with the water and in the air, the oxygen in the air, which is water in the air too. So it's reacting here, and as it turns from as the iron comes in, you have water coming in here, and you also have the hydroxide ion coming in, OH, you know, coming in as these are developing through, you're developing rust then. It's starting to rust away the steel. And you can see this is the electrochemistry of rusting. You can see how more oxygen, the oxygen is so important. And here you have the rust. Here's your chemical formula where you have the ferrous oxide, which is iron. Ferrous is iron with oxygen with the water, and how it's rusting out. So that's corrosion. So, and that's in the picture here. Let's see. Goes on and describes how salt water, it says electric current between anodic and cathodic sites is completed by ion migration. Thus, presence of electrolytes accelerates corrosion. So that's why you have like salt water causing corrosion to happen more. And this causes this pitting and rusting. And it usually starts rusting at points of strain, where there's a little crack or something, or some points of strain in the steel. That's where it's going to start really rusting out. So if you have that's why if you have a car, you know, that has been bumped, has a little car accident there, you know, that's where it starts rusting. How do we prevent this rusting? They have a few different ways of preventing. First of all, they can, to prevent, they can put a protective coat of paint. Certain paint, they paint over it so that the iron is not exposed to the air. It could be lacquer or grease or paint over it, and this will keep out the moisture. And that happens for a while until the paint starts cracking, right? So, and then the other is to make a contact between the iron and a more active metal. So if they take zinc, so that the oxygen will react with the zinc before it reaches the iron. That's all you're doing. Magnesium or zinc are both more active than iron. And so they have galvanized steel where they put, zinc or magnesium, so that it will take the reaction rather than the iron. Another is kind of a weird thing they do, but here we have magnesium sacrificial anode right here. So, and we have the sacrificial anode on an outboard motor. Why do they put that there? Because this will draw, will draw in, as for the corrosion, it will draw in like storage tanks, pipelines, and they're protected by making an electrical contact there. A piece of magnesium or zinc that's really close by will be placed nearby, and this zinc will bring in the oxidization process before it gets to the iron. So it's known as a sacrificial node, or sacrificial anode. So here we go. That's the end. So anyway, you just know what corrosion has to do with all of these processes, but it's a process you don't want to occur instead of you trying to make it occur. So this is the end of this chapter.